Good morning, ladies and gentlemen, and welcome to today's video. Today we're going to go over the 2020 sample exam problem that was published by College Board. And I think there's at least one part of this problem that I think is open up for some debate, and that is part B. So when we get there, we get there. But anyway, so there's a situation where students are conducting a study. They're comparing genetically modified corn to regular corn. They have 33 plots of land, and each plot of land is divided into two half plots. And then there's a random selection. So basically, genetically modified will be randomly placed in one of these two slots, and then regular will be placed in the other. And that occurs 33 times. All right, so there's like some sort of randomization going on here. Now below here we have some summary statistics from just these samples. So that's one thing that I want to make clear here. What we're looking at is one single sample of genetically modified growth or bushel yield, really, and one single sample of regular yield, right? So, and each of these had sample sizes of 33. The thing is, we're not told anything about the populations. We don't know that necessarily the population of genetically modified yields would be normal or otherwise. We're not told that the population of regular yields would be normal or otherwise. We're not given any information about the populations at all. Okay, so just keep that in mind. Anyway, going forward, part A says, explain why the yields from one type of corn are not independent of the yields of the other type of corn. So for this answer, I actually, I took one of the I borrowed one of the answers from the question stream, and I believe this was Selena's answer, and I kind of just modified it slightly. I said that each plot contains each type of corn. Consequently, both corn types are competing for the same finite resources. And if one corn is more aggressive/dominant than the other, in other words, if they use more resources, then it affects the yields of the other type of corn. Again, I believe that was Selena's answer, and I thought it was a very nice answer. Well said. And there are a few of you that said something very, very similar. So yeah, if you have that idea, then very nice job. Right, so just again, each plot looks like this, and there of course is a finite amount of resources in each plot. And so who knows, maybe the genetically modified corn is more aggressive and uses up the resources at a faster rate than does the regular corn. And therefore the regular corn will not have access to as many resources. All right, part B. And this was the one that I think was, for me, very debatable. Based on the summary statistics, would it be more likely to obtain a yield of 123 or more bushels per acre from a plot of genetically modified corn or a plot of regular corn? Justify your answer. Now, why was this debatable for me? Well, I was thinking about what exactly is this question asking? And it's a little tricky. Notice that they're saying 123 or more bushels per acre, right? So those units imply that they are referring to some kind of an average, bushels per acre. So they're basically asking for an X bar. So how likely is it for X bar to be greater than or equal to 123? In other words, what's the probability that X bar is greater than or equal to 123? And you'd really want to find this number for each population, the genetically modified population and the regular population. And this X bar is, of course, a sample mean. So if we were to obtain a sample of genetically modified corn, what's the probability that the average bushel would be 123 or more? Same thing, what's the probability if we were to take an average of, if we were to take a sample of regular corn, what's the probability that the average bushel would be 123 or more? Now, the thing is, it's great. Yeah, we want to find this probability, but we don't necessarily know what distribution where we'd be using. You might say, hey, isn't it the case that X bar is distributed normally with a mean of whatever the population mean is and a standard deviation of the population standard deviation over radical n? And yes, as long as certain conditions are met, that's true. But missing from this description is mu. We don't know mu for either population. We don't know sigma for either population. Now, we do have one single sample mean of genetically modified. We have one single sample mean for regular. We have one single sample standard deviation for genetically modified and one single sample standard deviation for regular. And perhaps I think it would be okay perhaps to maybe use those values as approximations for mu and sigma. And I think if you go about it that way, and if you claim that we're talking about samples that are greater, sample sizes that are greater than 30, I think it would be okay to approach the problem this way. And then therefore it would be okay to find your probability using the normal model. So I think that's one approach. I don't know if I necessarily like using a sample, one single sample mean to approximate the population mean and one single sample standard deviation to approximate the sample standard deviation, but oftentimes in statistics, we have to work with what we're given. And in this case, we're not given very much, and so perhaps we can argue that way. I think another way of arguing, I'm going to scroll down now. So just again, giving you an understanding of the situation. We don't know the population mean or standard deviation for either one of these, but what we do know are a whole bunch of sample pieces of information for genetically modified and regular. In other words, we dove into this population of genetically modified and we took out one sample of size 33 of genetically modified corn, and on average in that size sample of 33 plots, there were on average 125.018 bushels per plot. Same thing for regular, except that on average there were 120.482 bushels per plot. So again, you could argue now using a probability and a normal model. I think I guess that would be okay. Another way of arguing would be to, and this I think Justin suggested, another way of arguing would be to use the medians that are listed, because the question says, based on the summary statistics, answer this question and justify your answer. It doesn't say how you have to do it. So you can see that the summary statistics also contain medians, and it's very clear that the median of genetically modified is much larger than the median of regular. And in fact, the median genetically modified plot yield is much greater than that of 123, right? Whereas the median the median plot yield for regular is less than 123. So this right here is a pretty nice quantifiable argument. You might want to say something like 50% of the yields of genetically modified corn are 127.5 bushels or more, whereas 50% of the yields of regular corn are 119.4 bushels or more / less. Obviously, the median is the number that's right in the middle, so you can say 50% or more, or you can also say 50% or less. I I think an argument that I like is just refer to number of standard deviations above / below the mean. Again, this is using the idea, this is assuming that our mean and our standard deviation, the population mean and the population standard deviations are equal to our sample means and sample standard deviations. That's just one sort of assumption that we're going to have to make if we want to make this kind of an argument. So what I'm doing here is I'm sort of calculating what could be referred to as a z-score. I think technically really z-score is used if you're using a normal model. I am not necessarily using a normal model here. I can still determine mathematically the number of standard deviations above or below the mean. So give me one moment and I will calculate these numbers. Okay, and so after calculating these numbers for genetically modified, obtaining a sample mean of 123 is, well, observing 123 bushels per plot, that observation would be 0.851 standard deviations below the mean of the population, or at least what we're estimating to be the mean of the population. Whereas for regular, observing 123 bushels, that would be 123 bushels per plot on average, would be 1.401 standard deviations above the mean yield for regular plots. And so it's very obvious in this case to argue that genetically modified gives you the much better chance of observing that yield of 123 bushels per plot or more. Okay, so a few ways to argue. You can use a probability if you're using a normal model, and I think there is an argument for it. You can compare the medians, or you can compare figure out how many standard deviations this average would be from the population average. Of course, you need to use this formula where we have the observed minus mean divided by standard error. Standard error, of course, is standard deviation divided by radical n, because we are using a sampling distribution of sample means. We're analyzing a sample mean here. All right, that's part B. Part C, a little bit more straightforward. Describe the distribution of differences. All right, and that distribution is this guy right here. It's a box plot. Okay, box and whisker plot. One thing I want you to also be aware of is that we are given specific information. So even though looking at the scale, it might be tough to tell, the min, the max, the median, that outlier, it might be tough to tell that. But remember, we are given a table of values and we have the specific values for these differences, or at least for the important differences. So I think it is a requirement to, whenever you're citing like a center or a spread, some sort of quantity, you should list the specific quantity. So we'll go through this one quick because it's very similar to all these types of problems when we're describing a distribution. So I would start out with center, and I went on to say that the distribution of differences in bushels has a median of 3 bushels. Spread, the differences have an IQR of 6.9 bushels. And that was that the Q3 of 6 and the Q1 of negative 0.9. We're referring to differences here, right? So it's possible to have a negative difference, and that's okay. By the way, the reason I'm using median and IQR is because of the shape. And if you look at the shape, you can see that the differences in bushels are skewed right. Modality is not available, so unfortunately we can't mention modality, although in general it is a good idea to mention both skewness / symmetry and modality for shape. But in this situation, that is not available. I saw a few people ask, how can we tell about skewness? When we're looking at a box plot, it's all about the whiskers, right? So if we have this, as you can see, this right whisker is a lot longer than the left whisker, and that implies that this distribution of sample differences is skewed right. And as far as unusual features go, there is an outlier. One plot had a difference of 20.1 bushels. And I can safely say that it is an outlier because in a modified box plot, whenever you see a point that's detached from one of the whiskers, either on the high end or the low end, that point is an outlier. All right. And specifically, that outlier's value is 20.1. Don't say approximately 20, it is exactly 20.1 bushels. All right, that's part C. Part D, one of the conditions for inference that was met is that the sample size of differences is greater than 30. Explain why it's necessary to satisfy this condition. So part D, and you now go on to this hypothesis test situation. These are the two hypotheses. Hopefully you see that this is a matched pairs t-test situation. Okay, and basically the reason we need large sample sizes is to satisfy what's called the nearly normal condition. The nearly normal condition is what allows us to model the sampling distribution as a normal shape, or really in this particular case as a T shape. But these are actually very closely related distributions. As sample size approaches infinity, actually really much smaller than infinity. As sample size increases, T approaches the normal model, and it actually happens fairly quickly. Okay, so anyway, the bottom line is this sample size requirement is all about the shape. And so one argument you could say is that when studying sampling distributions of sample means, we want a sample size of at least 30 so that we can use the T distribution to model the shape of the sampling distribution. Now, I think if you said normal, you'd be totally fine here because, as I mentioned earlier, these are very closely related distributions. If you're still not sure why we use the T distribution, please check out my video that goes over exactly that topic, why we use the T distribution when we are studying sample means. Right? The key that I want you to understand here, though, is it's all about the shape. This sample size that is part of the nearly normal condition. So if we do have this large enough sample size, then we can ensure that shape that will allow us to easily calculate a probability of observing a sample average difference. And finally, part E, very straightforward. The test resulted in a p-value of 0.0003. Based on the p-value, what conclusion should the students make? A lot of you asked, hey, there's no alpha value mentioned. Should you mention alpha value? I do think it's an important thing to at least mention some kind of an alpha value or just compare p-value to alpha value, because in practice, that's what you would do. So what I said was, since this p-value of 0.0003 is less than any reasonable alpha value, we will reject H null. Now, that first sentence tells us what we do with the null hypothesis, reject it. The second sentence should always be something that sort of refers to the alternative hypothesis in context. So I go on to say, we have evidence to support the claim that the population mean difference in bushels per plot is not equal to 0. And how do I know that that's the alternative hypothesis? Well, if I scroll up here, that's exactly what this symbol is saying. The mean difference in bushels per plot is not equal to 0. And we definitely do have evidence based on the p-value to support that claim. All right, ladies and gentlemen, that is all. If you have any questions about any of these, especially about part B, please email me or post on the question on the Google Classroom main stream. I actually started a conversation or a topic post where we can discuss part B. I'm looking forward to hear what you have to say about it. All right, folks, that is all. And until next time, take care. Bye.